Cool, so linear algebra. Linear algebra is a branch of mathematics concerning linear equations, such as some constant a subscript 1 times a variable x subscript 1 plus any number of terms in the form a subscript n times a unique variable x subscript n equaling some constant b, or linear maps such. Okay, what does any of this mean? I mean, like, I could write that equation down, but why is it its own branch of mathematics? And what does this image to the right over here have to do with anything? And why can this article be translated into 90 languages? I didn't even know there were 90 languages. Linear algebra is weird in that there's kind of a big initial hurdle you have to climb to even understand what it is that you're doing. Even while I was studying it for the first time, I was just thinking, like, how could this be useful to anything? How could this solve any problems? But you're just gonna have to trust me on this. It eventually will make sense. So you remember in like Algebra 1 where you'd have those questions where it's just like kids' tickets are $5, adults' tickets are $10, they spent $55 total and there were 7 people total, and like how many kids and how many adults went to the theaters, and they would want you to set up this like systems of equations where you had the money equation that showed, like the number of kids times 5 times plus the number of adults times 10 equals 55, and the people equation, and you could solve it maybe if you're just like substituting for y, and you could plug it in. Or you could add a multiple of an equation to another equation, and then you would get the y and x. Or you could even graph it just because you have x's and y's, and then you get that x is 3 and y is 4, and that's your solution to the problem. These are already examples of solving systems of linear equations. This is the basis of linear algebra. But a lot of these methods are kind of oversimplified. These strats really only work because you have 2 equations and 2 unknowns, so there's one unique solution if you have those. Also, they always give the questions such that you have positive integer answers, so you don't have like negative half a kid. You may not have thought about it before, but if we introduced like a third class of people like students, and we said that they've spent $70 total and there were 10 people, then we can't solve this. There's no exact unique solution. There's already an infinite number of solutions to this problem. Or if all we knew is that there were only kids there, and we knew that there were 3 people, but that the money added up to 20, well, no it didn't. If there were 3 people, there were 3 kids, then it should add up to 15, so that would be like no solutions. Or if it did add up to 15, sure, whatever, that's our one solution, there are 3 kids. Basically, depending on the number of constraints of our problem, that's going to decide whether or not we can get one unique solution. And also, there's nothing special about making adults y and kids x. We can also just call these variables x1 and x2, so they're kind of on the same level, right? So this is how you would write these equations as a matrix, or rather, these equations are a conclusion you could draw from this matrix. Matrices, literally so simple. They're just anything we want them to be. In essence, a matrix is just a way of organizing numbers such that we have columns and rows, and how we interpret it is mostly up to the mathematician. For instance, usually when we have linear equations like this, we like to put this black line here to signify that, okay, we have the variable things over here and what they equal on the right. And here's some stuff that we can do to the matrix that's still going to preserve the answer, aka the correct x1 and x2 that satisfies these equations. We can multiply equations by constants. That's just the same thing we did in Algebra 1 when you would scale a whole equation by a number. We can add equations to other equations, obviously. You can swap the top and bottom equations, who cares, who cares what order they're in, you're gonna get the same x1 and x2. So what we can start doing is basically just solving the systems of equations through a number of row operations. I'm not gonna go too into what these row operations are or why I'm doing them, but it'll make sense once I finish it. So I could scale the top row by a fifth, I could subtract the second row from the first row, I could subtract the first row from the second row, and I just for formality's sake, I'm going to switch both of these. So this is what's called reduced row echelon form. Once again, I'm not really going to explain it, but let's just think about what this matrix is now. This is saying that 1 times x1 plus 0 times x2 equals 3, and 0 times x1 plus 1 times x2 equals 4. AKA, x1 is 3, x2 is 4. That's the same solution that we were getting earlier with our Algebra 1 things. Reduced row echelon form is something that you can just plug into your calculator, so it can just solve the systems of equations with one push of a button. Now, if you remember I said earlier, it's more just of a formality that we have this black line here. If you think about it, we could just say that the constants are actually coefficients of just some other variable, x3. We could say that constants are just scalar multiples of this variable, as long as it's the same variable. So that's why it doesn't really matter if that black line is there or not. We could even say that all of these are just equations that add up to 0 or something, and you would just have zeros on the right side of the thing, and those zeros would keep adding and subtracting to each other, not changing them because they're just zeros. These would all be mathematically equivalent It just depends on how we interpret them, or rather how we give them meaning. And that's the cool thing about it. Okay, you might still be wondering, what does this have to do with vectors at all? How do vectors come into play? So just in case you don't remember, I'm gonna go over a couple simple, easy, cheesy things about vectors. So vectors, in like physics, a lot of times you'll just see it as like magnitude and direction, like it's 13 units long at this angle. But in math, a lot more times you'll see it as in like component form. So it has 12 units in the x component, 5 units in the y component. And the way that we add vectors is just adding their x components and y components together to get, our final answer. Or geometrically, you could think of putting them tip to tail, just moving v over and then seeing the new vector that traces out. Both of those are the same thing. One other thing is just the fact that you can multiply vectors. Like I could just say like 3 times the vector u would give me 36, 15, and it would look like that, it would be 3 times as long. Or I could even scale it by a negative number and point in the opposite direction. You get the point. And let's just talk really, really briefly about vector spaces. A vector space can kind of be thought of as all of the linear combinations of the two vectors. So like if our two vectors were I hat and j hat, these are special vectors because they're 1, 0 and 0, 1. What do you think all of the points are that we could reach with these two vectors if we were able to choose whatever C1 and C2 we wanted, aka stretch these vectors to however long we wanted to and add them together? Well, I feel like the answer pretty obviously is all of the coordinate plane. If we had like some b, maybe 13, 7, then I could just say 13 times I plus 7 times j gives me b. Obviously b is in the vector space, and as it turns out, any two-dimensional b is going to be in the vector space for 1, 0, 0, 1, because I can just add them with different coefficients. But what might not be obvious is like, what is the vector space of uv? These aren't 1, 0, 0, 1. Will I be able to reach every single point in the coordinate plane? Well, the answer is actually yes. I still can. If I had my vector b again, it was 13, 7. As it turns out, I could add 1.158 u minus 0.301 v, and it would get me, 13, 7. As long as you have some in the x and y direction, you're going to be able to get anything you want with linear combinations of these. Now, obviously, there are some things that just won't work. If we have n and m that are, both just on the x-axis, we're never going to be able to add n and m together to get b. There's just no way to get up there. Similarly, if we have this other thing over here, this like 3D analogy, if we have these two red and blue vectors, we're never going to get off the plane. There's no dimension that's going to push me off the plane, just like in the n and m scenario. There's no dimension in the y direction that's going to get me up there. Basically speaking, n and m only span the x-axis. They don't span the whole coordinate plane. Okay, now that we kind of remember what vectors are, let's just do like an easy physics example. If we have these two vectors u and v, and these two like rocks are going to collide, and stick together, then you can just think of it as adding the momentums together. If I add the momentum of u and the momentum of v, then I'm going to get the momentum of my final solution. We'll just call that final solution b in this case. But what if I wanted b to be 50, 0? Like I wanted the final momentum to be 50 kilogram meters per second to the right. Well, then you could ask yourself, what is a linear combination of u and v? Basically, how much momentum would I have to give u and how much momentum would I have to give v in their directions to add up to b? Because in theory, it should be possible to reach any vector that I want in the coordinate plane. We would start setting up our equation. You can replace them, and you can distribute it in, because that's really what scalar multiplication is. You're just multiplying each of the components. So we have our x equation, we got our y equation, and oh, what do you know? That's two linear equations. We can write this like a matrix. So let's actually look at what's going on here for a second. The vectors have become the columns of this matrix. Our u vector was 12, 5. Now it's 12 over 5 in that matrix over there. V vector is a column, B vector is a column. When I interpret this matrix, I'm saying, what is the linear combination of these two vectors that gives me the vector 50, 0? Okay, so you remember when I said in this example that there were an infinite number of solutions? Well, we can kind of make that a little more specific. Like obviously one of the solutions isn't 0, 0, 0. We're gonna have to have more than one person to have this add up to 10 people. But how do we characterize the solutions if there's an infinite number of them? Well, once again, we have our constraints, we got our systems of equations. We can set this up as a matrix, but this time it's a 2x4 matrix instead of a 2x3. We can REF it, and now we have this matrix here. Okay, so what is this matrix saying? This matrix is saying x1 plus 0.8 x3 is 6, and x2 plus 0.2 x3 is 4. So basically, any set of x1, x2, x3 that satisfies both of these will be a solution to our question. But this isn't really an elegant solution. It's still kind of hard to tell what's going on. But maybe we can make it look a little bit better. I can solve both of these for x3, and now I can kind of combine them into this mega equation. Now this reveals that as soon as I choose something for x1, I get an x3. And as soon as I get an x3, I get an x2. I can really only choose one thing arbitrarily, and then I get a whole solution set to this question. If I chose that there were 4 students that were going, then I immediately know how many adults and children went. But once again, it's still kind of hard to tell what's going on. So one way to visualize the answer is saying, okay, our answer is one-dimensional. I just choose a number on the x3 number line, and then I get a set of solutions. But this still doesn't really feel like the full picture. Clearly there's something more going on than just looking at a number line and saying this is the best way to visualize it. So also what we can do is, we have our systems of equations, and those equations represent planes. Our mega equation here is a line, and if we graph that, then we can see that this line is the intersection of the 2 planes. Like the dark blue plane is our money plane. Every single point on this represents an XYZ, where the money adds up to $70. On the other plane, that's like the person plane, every single point on this, the XYZ add up to 10 people. And the intersection is where both of the conditions are met, where we add up to $70 and we add up to 10 people. And it's also pretty obvious from this that as soon as I choose an X value, as soon as I say, okay, it's the solution at X equals 4, there's only one point that could be. It is, I will get a C and a Y, and it's a line, which means that it's a 1D subspace of R3. Now this looks a little bit better than our number line from that other thing. Okay, that's probably enough for one video. There's still a ton to linear algebra that just would take too long to explain. Like eigenvalues, linear maps, determinants. I didn't even talk about how you multiply matrices with each other. But this should start to give you an idea that linear algebra is a powerful tool. It'll help you solve complex problems, especially when the dimensions go above 3 and you can't really visualize them. And yeah, hopefully you found this helpful. I don't know.
Play of the game.